Hello friends! Today I'm going to start building a brand new vintage 1980s Macintosh motherboard, made possible by the amazing reverse engineering skills of my friend Kai Robinson. Welcome to part 1 of the Macintosh SE Reloaded series. The SE Reloaded motherboard features gold-plated pads using a process called electroless nickel immersion gold, or ENIG for short. Plating the pads like this costs more, but it makes the board more resistant against oxidation, and apparently also makes it easier to solder components to it. Kai Robinson has authorized MacEffects to sell a glossy red version of this same board, also with gold ENIG pads. The Macintosh SE was introduced in March 1987, priced at $2,900 for the dual floppy drive version. That's more than $7,000 today. And $3,900 for one floppy drive and one internal 20 megabyte mini-scribe hard drive. That's right, 20 megabytes. Although the SE was intended to replace the Mac Plus, the lifespan of the Plus lasted as long as the SE. In August 1989, the SE was updated to a 1.44 megabyte floppy disk high-density version, also known as the Super Drive. But a year later, in October 1990, both the SE and the Plus were discontinued, having been replaced by the Macintosh Classic. The Macintosh Plus lasted so long in the marketplace because it served as a low-cost alternative to the SE. However, the SE offers a number of useful improvements over the Plus. For example, even though the SE uses the same 8 MHz 68000 CPU as the Mac Plus, Speedometer 3 shows the SE to be 12.5% faster. And Norton System Info shows the SE's CPU to be 18.6% faster. At the SE launch keynote, Apple showed how Cricket Draw was 25% faster on the SE compared to the Plus.
This program, Cricket Draw, from Cricket Software, run 25% faster than on the Macintosh Plus it was originally developed for.
For further reading about SE performance over the Plus, be sure to check out this very interesting webpage on the Unitron Mac 512. Both the SE and Plus have the same 4 megabyte RAM ceiling, unfortunately, but the SE has something special called PDS, which stands for Processor Direct Slot. The presence of that slot is also why it's called SE, which stands for System Expansion. Using that slot, you can add things like an accelerator board, some of which had their own RAM slots. By the way, the Macintosh SE30, a faster version of the SE, also has a PDS slot, but cards made for the SE30 are not compatible with the SE, and cards made for the SE are not compatible with the SE30. The SE was the first compact Mac to use ADB to attach keyboard, mouse, and third-party devices like the ArtPad 2 graphics tablet from Wacom. Previously, the Macintosh 128K, 512K, and Plus used a DE9 connector for the mouse and a telephone-style cable on the front for the keyboard. The SE also has SCSI 2, which runs at 660 kilobytes per second and is more than twice as fast as the Macintosh Plus, which is limited to 260 kilobytes per second. The SE was the first compact Mac to have a cooling fan inside. Previous Macs were cooled by convection. Perhaps the only downgrade on the SE was the PRAM battery, which is on the motherboard, unlike the 128K, 512K, and Plus, which made it much more convenient to replace the PRAM battery without needing to break open the Mac. So why am I even doing this SE Reloaded build, and why should you consider doing it? Well, in my case, I have a SE motherboard here, which was also very kindly sent to me by Kai Robinson, which has what appears to be water damage that mostly centers in the area of the connectors here, with a lot of rust in this area. But even more than that, on the bottom of the board, I would say that pretty much all of the copper traces on the bottom are very bubbly in appearance, and that shows that the copper is being eaten away under the green solder mask. which is pretty shocking, and that of course is why I need to rebuild this board on a pristine new motherboard. In your case though, it could be that you had a PRAM battery disaster where spilled battery fluid has eaten nearby components and the copper traces too. That actually served as the motivation for Kai to even do this project. Basically, this allows you to start with a pristine board. You can then take your old board and desolder the undamaged components and move them over to the new board. And for the components that are damaged, you can actually buy those online, either brand new or as new old stock. And that's what I did with this bag of components. Most of these are from Mouser, but I also purchased a large number from a place called UT Source. I put a link for you in the text description below where you can buy everything if you want. Well, you can buy more than 90% of the components. Some of the components you will need to move off of the board, and I'll go into more detail about that when I actually do the build. But even though a lot of components on this board are still working, it takes some effort to desolder them, and so to make it go along a little bit faster and to make my board truly look beautifully new, I decided to go ahead and buy a lot of the components that I'm going to need. But you know, things like these little push button switches, which are proprietary, you'll need to desolder those and use them. But most of them you can buy brand new. But before we actually start doing the build, I should mention that you will come across two different Macintosh SE logic boards. The older Macintosh SE motherboard is part number 820-0176-B, dated 1986, also with part number 630-4125 on it. This has older ROMs and a chip called IWM, which stands for Integrated WAS Machine. That is a floppy disk drive controller. The high ROM is part number 342-0352, and the low ROM is 0353. The IWM is 344-0043. These chipsets are only compatible with 800K floppy drives. They are not compatible with the 1.44 megabyte super drives. RAM configuration on this older board is set by resistors R35 and R36. The newer revision floppy disk high-density board is part number 820-0250-A, dated 1988, also with part number 630-4250. It has a high ROM marked 342-0701 and a low ROM 0702. This has a newer SWIM chip instead of the older IWM, part number 344-0062. The SWIM chip, in combination with the newer ROMs, makes it compatible with both 800K and 1.44 megabyte floppy drives. The RAM configuration is more conveniently set by a jumper named J16. The SE Reloaded board uses this newer revision. By the way, you can actually use the newer SWIM chip along with the older ROMs if you need to, but you'll only get 800K drive compatibility. The old ROMs and IWM chip can be used in the newer revision motherboard, and that is, of course, the same as the SE Reloaded board. The newer ROMs and the newer SWIM chip can actually be used in the older revision motherboard, although that doesn't apply to the SE Reloaded board. The old ROMs and IWM chip are compatible with System 4.0 and Finder 5.4, which was known as the System Software version 2 release. And that's kind of nice because there might be times when you want to use really old software. But the newer SE ROMs and SWIM chip require you to have System 6.0.3 minimum. It's now time to get started with the build, and here is my workbench setup. First of all, over here on the left, we have my bad board. We're going to use this for reference, and later on in the build, pull off some components that we need. I have flux here. Amtech is a pretty good flux. I also have MG Chemicals flux. Links to all of this will be in the text description. I have two different types of solder, thin and thick. Again, details of that in the text description. I have a Hakko soldering station. This one is the 937, no longer sold, but there's a newer Fisher-Price version that pretty much does the same job, set to 350 degrees Celsius. And then I have my little tip cleaner. I also have a wet sponge. I have a couple magnifying glasses to help me see. My certificate of authenticity proves that this is the real deal, folks. So this is the board on which I'm going to do the build. Then over here I have a list of parts that I constructed from Kai's BOM, and I will also link this for you. And I made time to put not only the component number, but also the location of where it is on the board. And then Kai suggested that we start with passive components, and that's what these are here, resistors, capacitors, and inductors. I'm going to start with these 0.1 microfarad capacitors because these are the largest in quantity, 51 pieces total, and I ordered very high quality X7R capacitors that are probably higher quality than the original, but that's okay. Now if you look at the old board, most of those capacitors are these little yellowish orange ones, but don't be fooled. If you count all of these little yellowish orange capacitors, you'll get 53 pieces. And that's actually wrong because the 0.1 microfarad capacitors are the majority, but there are two pieces, C18 and C19, right here near the crystal, which are of a different value. So they look physically the same, but if you take a magnifying glass and look at them closely, you'll see that C18 and C19 are different. So don't put a 0.1 microfarad capacitor in C18 and C19. Now before I go any further, I should mention that I have my board on top of this white piece of paper. This is actually A3 international paper size. I'm putting it not just to make it pretty, but because even though my wooden desk here is very smooth, it's a little bit more jagged than this paper, and I don't want to scratch this pristine board, so I'm using the paper here so that as I flip it over and back multiple times, there's not going to be any scratches on it. Now when cutting the capacitors off, be sure to keep in mind that you don't want to cut the leads too short, because as you can see, we're going to need to have extra lead length in order to come out from the body and then go through the holes, and then you want to have some extra lead length once you go through the holes. So making the leads much longer than you need is perfectly fine, and cut them off, I guess, more than a centimeter on either side, so you don't have to worry about having cut off the leads too short. I'll go ahead and just start with C1, and we need to bend the leads. Now there are different ways to do it, but probably the best way is just to eye it and then take your capacitor and bend the leads to be 90 degrees. We could take some pliers to do a better job, but that would take a bit more time. We got 51 pieces of these, remember? So it doesn't look too bad that way. Alright, here's the flip side of the board, and you can see that I bent out the leads just very slightly in the opposite direction to keep the capacitor held in there. And I'm going to try it without any supplementary flux, and let's see how these gold Enig pads do for us. Because most of these fluxes have a little bit of, most of these solders have flux in them already. And for the sake of speed, if we don't put any excess flux on, then it works fairly well, even without the excess flux. And flipping it back over again, we see our capacitor. Note that some solder came through on this side, which makes it look nice and neat. On this side, though, there wasn't any excess solder. Technically, you don't have to add any because it's a through hole, so it's making contact because we soldered it on the other side. But if you think it's prettier, we can add more solder here to make it match. Now, it will make it easier for us to flip the board over and back a lot of times if we clip off the excess leads, and since we have it soldered in good, no reason to leave them. So we'll just cut them short. And I cut one a little bit shorter than the other one, but that's okay. About this length is just fine. Now before I jump in and solder in the rest of these capacitors, note that this is the BBU chip, and in the upper left corner there's capacitor C67. Now it says optional, but after consulting with Kai, I've learned that it is definitely not optional. You should not install a capacitor in C67. That kind of goes without saying because on the stock board you can see C67 is not populated. Kai installed C67 and tested, and he found that the picture on the CRT was shifted horizontally to the left, and it also had some artifacts as well.
Why is the video doing that?
After removing that capacitor, everything was back to normal.
Problem solved. C67 on the original logic board. Turns out that actually it's not needed at all. Having looked through the schematics, very strange. I couldn't figure out why it was trying to clamp H-sync to ground. So, removed C67, and you can see the raster is behaving itself.
All said, you don't want to install it, so make sure you don't put anything there. And earlier when I told you that there were 51 pieces of capacitor, that does not include C67. So 51 pieces is correct. And one last thing before I start putting all these capacitors in. These are ceramic capacitors, so they're not polarized. Therefore, it doesn't matter if you flip them and put them in the opposite direction. There is no polarity. It doesn't matter. And finally, the last one. And ta-da! All 51 pieces of the 0.1 microfarad capacitors are installed. Okay, now that I'm done, I can check that off, and we still have the rest to go. So I'm going to now install C18 and C19 and C40. These capacitors are great because these are COG. We can see that here. And we really don't need these voltage ratings. It's just what was available at Mouser at the time. But the reason why these are great ceramic capacitors is because they don't have a voltage D rating, which is different from other lesser grade capacitors like X7R. X7R is actually a high grade capacitor, but still not as good as COG. Unfortunately, COG doesn't come in large sizes. It comes in picofarad or low nanofarad sizes only, and has no voltage D rating. So if you put in an X7R with a voltage D rating rated at 25 volts and you run it at 25 volts, you're probably only going to get 20% of the capacitance value. Yeah, that's just the way those capacitors work. But these are special ceramics with COG, and if you run a 25 volt COG at 25 volts, you're going to get the full 10 picofarads, as you would expect. So anyway, you don't need to worry about that when putting them in, and where to put them in is what I've put here in the location. C18 and 19 are both at C9, and E4 is the location for capacitor C40. Now, unfortunately, on the SE Reloaded board, on the left side, there are no letters, and on the bottom, there are no numbers. But on the stock board, we have A, B, C, D, E, F, all the way here on the left side, and then we have 1, 2, 3, 4, 5, 6, all the way to 12 at the base. And this is great because, as I just said, C18 is located at C9. So we say C is a row, and then we go over to 1, 2, 3, 4, 5, 6, 7, 8, 9, and there we go. And it tells us approximately the area that we need to be. So C18 and C19 are right here. And then for the C40 capacitor, we know it's E4. So A, B, C, D, E, and then 1, 2, 3, 4. So we kind of zoom in here, and E is about from here to here. So it covers this whole area, and then 4 goes this. We can see that C40 is here. C40 is a glass encased ceramic on the stock board. So here's C18, and you can see it's roughly the same body size as the 0.1 microfarad capacitor right above it here. And that's because, again, this is rated for 100 volts, so it's a bit bigger than you'd expect it to be, and we're going to solder it in right there. Now for C19, our 10 pico. And C40. Okay, it's time to mark off C18, C19, and C40, all finished. Now we just have to do all of these resistors here. Now before I just jump in and start doing it, I want to say a few words here. The resistors here are all 1%. They have these little blue bodies here, plus minus 1%. So for example, in the case of 10K, this could be 1% higher than 10,000 ohms, or it could be 1% lower than 10,000 ohms. So plus minus 1% is the tolerance. And that is actually better than the stock resistors, which have a 5% tolerance. So Kai Robinson recommended to me to go with the 1%, and that was good advice, because what I found was that when I was purchasing 10K resistors on Mauser, they didn't have any. Yeah, incredible. They were out of stock, and for months into the future. And so I had to buy 10.2, and you might say, oh, is that going to work out? Well, actually it is, because these are 10.2K at 1%. So even if it's 1% higher than 10.2K, that is still within the 5% tolerance of the stock resistors, so it's not going to be a problem at all. And that would technically apply to any of the other values here, if indeed you needed to substitute with a very slightly higher or very slightly lower value, so long as you do the calculations and determine that the upper 1% tolerance limit or the lower 1% tolerance limit is within the 5% tolerance of the original resistors, then you will be fine. The only other note applies to R39A and R40A. I mentioned that the left side resistor leg has to be soldered into the rightmost pad. I'll stop soldering in resistors and comment on that in a few minutes so you can understand what I mean. I'm stopping here because of resistor R39A and R40A. They're special. You don't want to solder in the left leg into the leftmost pad for either one of these. As you see here, this is the stock board you're looking at. You want to solder in the left leg into the rightmost pad for each of these resistors. Now on the right side, it doesn't matter because both of these pads are connected together. Both of these pads are connected together, but for the sake of consistency, you might as well solder the rightmost leg in the rightmost pad for both of them. In other words, on the SE Reloaded board, just like you see here. Left leg, rightmost pad, right leg, go ahead and solder it into the rightmost pad. I'm now going to solder in the remaining resistors without stopping, and then after that I will do the 2 inductors, and I will at that time pause and make a few comments on them. Okay, now before you say, hey, you forgot to populate R33 and R32, actually I didn't. As you can see, they're not populated on the stock board either. Okay, so what about the inductors, L1 and L4? You'll see here that I have 2, and the reason why is Kai was telling me that some boards have 27 microhenries and other boards have 33 microhenries. And Kai was saying he's seen a lot of US-made boards with 33, but most of the European boards with 27. However, when I search for photos of the SE motherboard, almost all of them are 27. So it's probably good if you buy a replacement to go with 27, but I bought a 33 just in case. Probably I won't be able to tell any difference. But anyway, the L4 here is a ferrite bead. Well, first of all, here's L1, so you can see from Mauser. These are 5% tolerance. The stock have a silver band, which means 10%, so these are a little bit better. And then L4 is actually a ferrite bead, and that part number is probably what you need. But if you look at L4 on the stock board and then compare the body size to the replacement, they don't quite match up. So I'm sure that the properties are not quite right. It's probably okay to use that, but if in doubt, you can desolder the one on your stock board and use that. The same applies to the inductor at L1, because if you look at the body size of the replacement, well, The stock is much larger, so it probably will be okay, but I've not tested it yet. And again, when in doubt, you can use the stock one. This board was immersed in water, and you can see the leads are really corroded, so it's probably better if I use a replacement. But on your board, if the leads are pristine and it hasn't been water damaged, then you might want to extract it and use the factory. And to close out this part 1 video, I'm going to install the medium, what I classify as medium passive components, a little bit larger than what I just installed. That includes all of these Axial capacitors, and also RP1 and RP2 resistor blocks, and Q1, which is an NPN transistor. Now, before I solder in these replacement Axial capacitors, I wanted to check the ESR and also capacitance, so I'm checking C36 in circuit right now, and well, it's 1,907 nanofarads, which is 1.9 microfarads. Now, it's supposed to be 1 microfarad, so that's quite a bit unusual. But the worst part is that the ESR is 0.668 kiloohms, so that's 668 ohms. I think I need to desolder this from the circuit to make more accurate measurements. Also, all of the other capacitors are 33 microfarad, and they're connected together. So I definitely can't test them in the circuit, so I'm going to desolder one of those too, so I can make good measurements of both. The leads are bent inward instead of straight, so to make it desolder easier, I'm going to straighten them a bit. I'm applying some fresh solder on it in hopes of loosening it up, and it's not even melting. So, I mean, I could just clip it off at the leads since I'm not even going to use it, but this will be my first test to see how effective I am at desoldering components on this stock board. Again, it was immersed in water, so I'm not really surprised at the trouble here. This also could be a ground plane maybe on the other side. I'm not sure, but man, it's not wanting to come out of that hole. Solder mask seems to be coming off of the traces. Well, it doesn't look like I'm being very effective here. Let's try the other side and see. Okay, that seems like that side may have come out. The tray seems to be gone. I can't, I'm not using my microscope to check, but let's see here. All right, that one came out. Okay. Now the other side. Got him out. Great. Okay, so removing it from the circuit does make a difference. We're getting spot on 1 microfarad. 999 nanofarads is 1 microfarad. And the ESR is a more reasonable 15.2 ohms right now, although still a bit high, maybe. What else? If we push our button here, the angle is minus 89.3, which is about normal. Dissipation factor 0.011, and the Q is very high, 86.9. Okay, so let's take my 1 microfarad replacement. Interesting. Well, this is spot on in terms of capacitance, 1.08 microfarads. ESR is almost 31 ohms. Now this is being done at 120 hertz, which is typical. If we increase the frequency that we tested at, then of course the measured ESR value will go down. But what else? About the same angle. So dissipation factor is higher. I'm not surprised by that. Quality is lower, 38.9. So it would appear that even though the board is water damaged, the stock capacitor is maybe even higher quality than replacement. Very interesting. Now, if we go back to ESR and then I change the frequency to 1 kilohertz, we see it drops down to 8 ohms. 10 kilohertz, it's 2 ohms. 100 kilohertz, it's under an ohm, so 900 milliohms. And if we swap in the capacitor we had before, and now again, this value of capacitance has changed because we're doing 100 kilohertz now. So at 100 kilohertz, this is 1.4 ohms. So it's higher than this one. If we change the frequency to 120 hertz again, so 15. So it's about half of the ESR at low frequencies. And then change it to 1 kilohertz, 4, 10 kilohertz, 2. So, and then 100 kilohertz, 1.5 now. So the frequency difference here is apparent. So at higher frequencies, this replacement is doing better. Well, it's not going to harm anything to use this, and technically speaking, we really don't want to use these old capacitors anyway. Arguably, this SE probably wasn't laid down on its side, and there's no sign of leakage, but they're just so old, despite what we've seen here, we really shouldn't use them. Now I want to check the other one here. This is a 33 microfarad. All right, let's go back down to our standard 120 hertz. Not surprising, the ESR is lower because higher capacitance, you tend to have lower ESR, 4 ohms. And we're getting 34.6 microfarads. So higher capacitance than what we should be seeing, but that's not a problem. It's actually a good thing, I think. Let's see. Angle minus 83. Dissipation factor 0.1. Q is 9. Okay, change frequency to 1 kilohertz. 1.6 ohm. 10 kilohertz. 1.3 ohm ESR. And 100 kilohertz. 1.13 ohm. Okay. So again, just in case we forget here, the 120 hertz is 4.1. 1.1 and 1.4. Okay. Snag a replacement. Okay, so lower ESR at 100 kilohertz. Let's go to 120. All right, so we're getting about 32 microfarads. So this has less capacitance, but it's within tolerance, so you shouldn't panic if you're going to test yours. And by the way, this meter is one of the best LCR, inductance, capacitance, resistance meters you can get. The DE5000, I'll put a link for you in the text description below. The kit I got included this TL21 adapter. There are other adapters. I'm not going to go into detail on it, but it's just a great, very accurate meter. So we're seeing 4.7, so not dramatically different than the old capacitor in terms of ESR. Angle about the same, dissipation factor about the same, Q is about 9. So okay, change frequency to 1 kilohertz, 1.23, 10 kilohertz, 0.84. So at higher frequencies, the ESR is lower. Not dramatically lower, but lower. So what do these tests tell us? Well, it tells us that these stock capacitors, despite the water damage, are surprisingly okay. We will only know that in practical use, but all the data that we're seeing here suggests that they should actually be okay. I didn't test all of them, of course, but the one I did test is probably indicative of the others. And the replacement capacitors, even though their ESR at lower frequencies is higher, especially for this 1 microfarad, it should still be okay for the use on this SE motherboard. Okay, got C36 here. We want to make sure that our polarity is correct. Kai marked them. You can see the plus signs, so that's going to be on the left. And there's actually arrows. In this case, it's pointing to the right, which is correct. So it says minus is over here to the right, and that means this is plus. So this is a 1 microfarad capacitor, and that's going to go in C36. All right, we need 10 pieces. 10 pieces, 2, 4, 6, 8, 10. Okay, 10 pieces of 33 microfarad. Next, we want to do RP1 and RP2. These are 39 ohm multiple resistors inside resistor blocks. Now, the key to installing these correctly is to note that all of the pads are circular except for one. And you can see that this one over here is square. This square pad is square because it needs to match up with the dot on the actual part that we're going to install. So you're going to put this pin with the dot into the square pad here. And that applies to RP1 as well. And this is how it looks on the stock board. Now I put a little lens cap here directly underneath this part because it wasn't being pushed all the way to the board, and by putting a little part or something flat underneath it, it's going to push up on it so that it's not going to be standing up on its legs. The body will touch the board, and that's what we want. And we want to make sure that the pins are coming straight up so that the part doesn't go in at an angle. And last but not least, we're going to install Q1 transistor, which technically is not a passive component like capacitors, resistors, and inductors, but it is small like these components, so that's why I included it in this category. And this is showing you the way it goes in. You want to make sure that the flat side of the body is facing this way and the curved side is facing that way. I have to spread out the legs a little bit. Don't force him down too hard, but he will be standing up on his legs. And here he is, all soldered in. And that's it for this part 1 video. I'm going to try my best to get part 2 out to you as soon as possible, and at the same time I will create a playlist in which I will put this part 1 video and my part 2 video and all subsequent parts of this video series. I'm not sure how many. I might do 3, might do 4. I think I want to do the testing in a separate video at the very end, but ultimately all of them will be in a playlist. It'll be very convenient for you to find all of the videos, and very nice because if you like, you could play them all back to back that way. Also, be sure to not overlook the text description under this video, so be sure you're watching it on YouTube so you can scroll down and you'll click Show More text on a desktop computer to expand it out. I spend a lot of time putting that together for you. It's not only things that you can buy on Amazon, things that I've referenced in the video, but also a lot of information and resources that I just can't fit in this video either. So please be sure to look through that, and I'm sure that you'll find something that's useful that wasn't already contained in this video. And that's true of all of my videos. I always fill that text description with as many characters as they will allow me to do. I try to anyway. And next, I'd like to thank 5 very special people who generously contributed to this channel in the months of April and May this year, starting with Philippe from France. Thank you very much for your donation, Philippe. Next, I'd like to thank Joe Williams. And this is not Joe's first time donation either. Joe donated several months ago, and he's following it up with another donation this month too. So thank you very much, Joe. I appreciate it very much. And next, I'd like to thank 2DFX. I certainly appreciate your interest in this channel, so much so that you gave a very generous donation. Thank you for that. Next, I'd like to thank Daniel from Hawaii. Daniel, by the way, the last time I was in Hawaii, it's been a number of years, 1998 actually, when I had my honeymoon. Beautiful state you're in, I must say. I went to Maui, and I'm not sure where you're located, but I've always wanted to go back. I just haven't had the time. So, since you're already there, enjoy it. Next, I'd like to thank Mauro Aciacaferi, a name that many of you know well if you've watched my other videos, because he is a monthly supporter of this channel. And Mauro, I truly wish to say thanks from the heart, because every time PayPal sends me a notification of a new donation from Mauro Aciacaferi, I'm just really touched. I don't expect it. Because again, you're the only person who does that, and I really appreciate it very much. So thank you for your ongoing support. And last but not least, I'd like to extend special thanks to the gentleman who did all of this amazing reverse engineering, Kai Robinson. He donated a lot, not only just his reverse engineering efforts, but to this channel. He sent me 2 of these beautiful matte black boards, but he also sent me this lovely navy blue, also with gold nig pads. And I must say that, you know, the black is beautiful, but so is this blue. It's a glossy blue, and just it goes beautifully with the pads. And of course, on MacUFX, you can get a red version. I believe that's glossy as well. But just a beautiful, beautiful work. He also sent me this amazing shirt too. You can see the beautifully embossed Apple logo, SC Reloaded team on it. I really appreciate that. But he also sent me not only that, but he sent me a batch of components as well. Not every component I need for the build, but a lot of very useful ones, including some custom PCBs that he made, and I'll introduce those in a subsequent video in this series. He sent me a lot more than that. He even sent me the defective bad SE board and other things too. He also invested a lot of time because I asked him a lot of questions, and he's very good about answering those. So thank you very much, Kai. And by the way, if you ever run across Kai on the Tinker Different forum or on Discord or wherever else online, be sure to give him a digital pat on the back and just say, man, job well done. Because in terms of this SE Reloaded project, that's how I feel anyway. Just an amazing, amazing engineer. And now it's time for me to thank you folks for watching today. I really appreciate your time. I always enjoy your thumbs ups, your subscriptions, and especially your comments down below. Please let me know your thoughts, and stay tuned because part 2 is coming out soon. I look forward to seeing you then. Take care.